I believe we should start. It's about time. I just want to thank everyone for joining us today, and thanks, Adrian, for being our host today. I just want to say that we as Crafting Software, we are doing Erlang and Elixir because of Adrian, so I think this says everything. So thanks once again, and yeah, please join. So we can start. Thank you, Adrian. Good luck.
Hi, I'm Adrian. I'm a senior staff software engineer at Outreach. I've done a lot of Elixir, Erlang back in the day, not so much currently, but as Gabriel said, I kickstarted like using Erlang and Elixir at Crafting Software. So I guess that's why I'm here. The talk I'm giving today. Okay. Yeah. So it's a mix of multiple talks. So for people that actually are familiar with Erlang Elixir, some of the concepts should be pretty. Actually, this is a good. I know that people that are online, most of them are familiar with Erlang and Elixir. From people here, anyone used like Erlang Elixir in the last 10 years? Okay. The usual suspects. Cool. So no, it's good that we have people that didn't. So it's good. Okay, so the talk I'm going to talk to you today actually about how can we build fault-tolerant systems in a pragmatic way, and I'm going to point out why in a pragmatic way. We have many ways to build systems, right? We can go pretty wide and far on how we compose our systems, what components we use, and basically how much we over-engineer our system just to be fault-tolerant. And there are multiple approaches, so we have to see what's pragmatic for us to use in the context we are now, like the project is right now. Okay. Yeah, also about me, almost 20 years of experience. I've been paid to program in like C#, Java, Python, Erlang, Elixir, Haskell, Ruby, Golang, and a couple others, probably I forgot. No. I would have remembered. Okay, so agenda of today. First, like what's fault tolerance? This is going to be just like a textbook definition. Talk a bit about availability. Then like rules, core principles we need to follow when we try to build fault tolerant systems. And then how we can use like an actor model based language to build fault tolerant systems, and basically what's unique about it in a way, right? Because yeah, we can build fault tolerant systems with any language because all of them are like Turing complete in a way, but each one has its own pros and cons. And at the end, a nice demo and Q&A if there are any. Okay. I'm not gonna read all of that, but basically the gist is we want our system to survive errors, right? So we, as programmers, we invest a lot of time and energy trying to prevent errors, somehow thinking that they're not gonna happen. Whatever we do, like machines fails, network fails, partitions, like network partitions are happening, I don't know, AWS goes down. A bunch of stuff can go down, which is not under our control, right? But still we program as if all these are forever and there and always working, which is not true. So, and the best we can do is then to partition our system such in a way that if parts of that system starts failing, the rest of the system still works. And our users actually are not panicking. Okay. So a bit about availability. Usually you have SLAs around it, depending on the business you are in. If you're like a startup that, I don't know, creates a new product that maybe, I don't know, it's newish, like on the verge of not existing yet, probably your customers are not going to complain if it's down from time to time. But if you create software, I don't know, either for like healthcare or for like aviation, as we see right now, that this is a problem, you want your availability to be really, really high, right? You don't want to be in the situation where the plane cannot land because I know I have to do a deployment. Okay, so, and yeah, in my experience, I've been through a lot of, let's say, I remember the days where it was fine. We were just each Friday restart the servers, have like full day, maybe, I don't know, blackouts, no activity on the application because we're doing rollouts and stuff like that. Like for banks, that's pretty normal. Even now, they have over the weekend, they put like a nice banner, website down, and they are doing their rollouts. But there are a lot of systems where this is not allowed. It's like you cannot exist if you do stuff like that, right? And what's important about this is like actually one is maybe to take the system you're working on right now and try to figure out, okay, actually with all the deployments and all the incidents we had this year, how much time did we spend like in an off state? What was the downtime, the downtime of our system? And then you can figure out actually how many nines, right? And maybe you have like bragging rights when you go to beers and stuff like that. Okay. But what's really important to note is that the price grows exponentially as you go down, right? The more availability you want to have, the price you're paying for your infra, for all the toolings, for like SREs and everything increases quite a lot. And from my point of view, right, the sweet spot, right, is usually it's in the middle. But right now, with the kind of existing mainstream tech stack, reaching the middle is quite hard, even with like Redmi deployments and all this stuff. Okay, so we want to build a fault-tolerant system. What kind of like properties do we want our system to have in order to be fault-tolerant? First one, we want isolation. We want any error that happens in the system to be sure that it's contained. Where it happens, okay, we can try to either fix it or restart it or whatever. But we want to be contained, right? And unfortunately, what to say, right now, the state of the art, in a way, for a lot of systems is like, oh, we have Kubernetes. If there's an error in one of our pods and something is wrong there, we don't know what's happening actually, because maybe you don't have enough traceability or whatever to look at it. It's easy, we fix it, we just restart the pod. And somehow our isolation level right now is like the pod, right? More or less that in the same time, okay, this works for sure, but it's not pragmatic and it's not efficient because you might have a lot of stuff happening on that pod. You might have a lot of long-lived connections, maybe restarting that pod and recreating it and reestablishing all the third-party integrations with like API calls or whatever. Maybe you have a big cache, you have to rehydrate again, right? So just the fact that you can restart the pod to start from like a well-known state doesn't mean you should. Or like, okay, you should if you don't have any other way of achieving that. But there are systems that you can achieve this in a much simpler way, okay? So yeah, and when we have isolation, then automatically we have fault tolerance because that means if an error is isolated, the whole system can just continue processing whatever it was doing without stopping the world, right? And I don't know, depending on the language that you are working on, is it like a panic? Is it like whatever that forces you, right, to restart, right? And because you don't have proper isolation at the VM level, automatically, because you don't have any guarantees what's the state of the memory when whatever fault occurs, you could try to pretend, okay, let's try catch it and continue, but then at that moment, your memory is corrupt. So sooner rather than later, instead of, actually stop that part of the system and restart it, and restart it from like good memory and good state, you're just created an issue that, I don't know, in 1 hour from now, your system is going to crash from a totally unobvious reason, right? Automatically, if you have isolation, that means that you have scalability, because if things are isolated, it's pretty easy to scale them, right? Horizontally, you just start more of them. Right? It's easy to test, because if things are not isolated, you know, when you're doing like integration test or unit tests or whatever. The hardest part is actually cutting down all the third-party dependencies so you can test things in isolation. But if you have a system that offers you isolation by default, then the whole testability problem gets much, much better. Okay? And also, it's easier to comprehend, right? Because when things are isolated, that means you can understand by piece, right? Okay, I take this thing, this process, I understand what's doing. I take this process, I understand what's doing. And then you just have to figure out, okay, what's the communication between them? And yeah, when you have multiple running isolated components, you can upgrade them individually, right? You don't have to stop everything just to upgrade parts of the system. And yeah, more or less, what I'm describing right now sounds like microservices. It is microservices, but you will see there are multiple levels of achieving this in simple manner. Okay, we need concurrency, right? And why we need concurrency? Because the world by itself is concurrent, right? At any time, the world around us, multiple things happen in the same time, right? Using a sequential execution, you could never actually model that, like the real world. So you need concurrency. And for concurrency, we have multiple ways of achieving concurrency, like threads, like greenlets, like, I forget what JavaScript, like all the throw things away, sorry, like the callbacks, hell, right? But what's important to note is like there are two terms, right? Like concurrency and then parallelism. For concurrency, it's like you can have concurrency with only one executing unit, only one core. And all that is doing at that point is like your VM is continuously switches between tasks. Okay? You stop, you execute, you stop, you execute. If you want parallel execution, you need at least 2 or more executing units, like more cores. Only then you can actually have 2 things happening at once. With concurrency, you can have, when you have only one core, at any given time on your machine, even though your system looks to be doing multiple things at the same time, actually just executing only one. Okay, detect failures. To be able to be fault tolerant, we have to actually be able to detect that a fault occurred. Right? So, and I know that a lot of this that I'm saying is like, I'll say, common knowledge or like simple knowledge. But what's important when we talk about fault-tolerant systems is that we are forced to think about multiple machines, right? It's not, we cannot say that we have a fault-tolerant system and, I don't know, all our eggs are in the same basket, right? Because the machine can go down, the region can go down, the data center can go down. If you have to actually have fault-tolerant systems, you have to think about, okay, how is this distributed across the globe, in how many data centers, all that stuff, right? And also, what's really, really important is to be able to detect the failure, right? Because then it's the job of another machine to actually figure out, okay, failure occurred, now what? If the machine didn't go down, then okay, most probably it's able to fix itself, right? Start from a well-known state and continue executing. Okay, fault identification, nothing here to see. It's just, okay, what type of error was thrown. And not the last, you need to be able to upgrade your system while not stopping the system. Right? And this, let's say, as I said, the spectrum is pretty wide here. You have systems where the system is down for hours or days until it's back to like everything is upgraded, because that's the definition of like all the components are like, or better said, our system we know and we tested that works only with this version and this version and this version and this version. And then we stop everything and bring the system to that new version. But for fault-tolerant systems and live, let's say, real-time systems, you cannot do this. You have to be able to upgrade your system while it's running. And yeah, we use stuff like red-green deployments, using a load balancer, switching traffic from another. You have multiple ways of achieving this. In the same time, yeah, it's, let's say, it's a tough problem in a way, right? Especially if you have nodes. Think about, for example, for MMO, right? You have a server for like a massively multiplayer game, right? Automatically, that server means they have maybe like millions of connections to it. You cannot just say, oh, okay, I'm gonna do continuous deployment. So each time someone commits something to master in like 2 hours, it's live. If your strategy, okay, you can do continuous deployment, but if you don't have like live code upgrades, that means each 2 hours, your system or all your clients will have to reconnect, right? Because you're stopping the server, you have to redirect those connections to another instance, everything, right? And you can go into like thundering herds problem where you have millions of connections connecting to one server, that server crashes because too many connections, you go to the next, that one crashes, and then you're DDoSing yourself, okay? And that's why live code upgrades are quite important for a lot of systems. Not all of them need this, but at the same time, if it's free and if it's built in, then yeah, why not use it? And the last one, basically, yeah, you need stable storage. But 20, 30 years ago, this was like a problem, but now, especially with like cloud solutions, like we are using like, I know, RDS automatically has the replication, multi-AZ, all that stuff, right? So right now, when you're building like a system, you're not necessarily concerned that, oh, okay, maybe my database is gonna go bust. Because you know that, okay, automatically you have like replicas, you have readers, writers in multiple regions, all that stuff, okay? So yeah, it's pretty simple, right? I mean, 6 principles to build fault-tolerant systems. At the same time, we spend our lives doing it, and still somehow it not feels necessarily simple, right? But yeah, I have like a silver bullet for you. I'm joking. It's not a silver bullet, but from my point of view, it's right now is the best way to build fault-tolerant systems. As I mentioned before, I work with quite a wide range of technologies, front and back end, and in the last 10 years, I focused more on back end. But yeah, right now there's nothing better than the way that the actor model is actually implemented in Erlang and Elixir. And I'm gonna try to argue my way through it. Okay, so what's Beam? Right? So Erlang and Elixir are functional programming languages that run on the Beam. Beam is like the virtual machine for Erlang. It was started to be built in like in the 80s, 85, something like that. So it's quite old. It's not like some newfangled technology. It's like almost 40 years old. What's important about it is that it was built for telecom systems, where they did have these constraints that they have to keep the system alive all the time. So, okay, I'm doing a rollout. Oh, by the way, I cannot interrupt the existing calls. Right? But the code has to be updated. So what they've done, they've built a virtual machine from the ground up with the first constraint for them was it needs to be fault-tolerant. All the languages that we have right now, except like the Beam, they were more, the constraints were different. Were either like, how can we run as many CPU cycles as fast as possible? How efficient it is like C, C++, whatever, right? With how nice it is to interact with it from a programmer point of view, like what's the ergonomy of the language, and I'm talking about, Python, Ruby, whatever, in that class of languages, maybe Go, which is in the middle. But this is the only VM and the only set of languages that were built for fault tolerance and for massively concurrent systems. And how to say, a lot of people kind of slipped on it because there was no use until 2025, until 2005. No one kind of used Erlang because, except like Ericsson for their switches and everything, because everyone was like running on a single core. And when you have like a single core, you can pretend that with locks and mutexes and threads, you can sort of have like concurrency. And you can pretend for a long time, right, that at some point you start to get really tired about the race conditions and deadlocks. But yeah, you can pretend for a while. The thing is that in 2005, right, we started to get multi-core. And at that point, we couldn't actually hide from the fact that actually we need to execute to be able to use the machines we have at our disposal as efficient, as best as possible. we need to do concurrency. And it was clear then that just using threads is not enough. Right? And then, okay, this Beam and Ericsson had a solution like 20 years prior to this for this, but it was like a coincidence. They didn't build like necessarily for like the web. They built it for telecom switches, but the whole same execution model and the whole concurrency model actually now scales like crazy in the web. Okay, so what's interesting about it? Basically, depending on the number of cores your machine has, you're gonna have like as many cores you have, as many schedulers you have, and then you have like a pool of like processes that are scheduled on these schedulers. By these schedulers directly on the CPU. What's interesting to note is like all of the programming languages except this, right? For example, Golang, right, has something pretty similar to this. The difference is that Beam is the only VM that is actually preemptive. What this means is that each process that executes in a scheduler, it's allowed to execute only for like a specified amount of time. To be sure that it's able to offer this soft real-time guarantee, basically any process, it's stopped, literally stopped. For example, if this process starts executing, I don't know, 400 nanoseconds, after 400 nanoseconds, it's stopped, another process by that scheduler is picked up and continues to execute. Think about like in, I don't know, either Go or like C#, Java, whatever system. If you have one of your threads in your application ends up in like an infinite loop, automatically that infinite loop brings your system down. There's no way around it because the VM, all the VMs except Beam are like cooperative. That means you always have the process that executes something. When it finishes executing something, it has to yield. Right now, we don't do necessarily yield in a manual manner, right? We just, okay, task async, whatever, execute this, or coroutine that, and then we know that at each time when we are doing some I/O, that coroutine is taken out of the scheduler, another coroutine starts executing, right? Or like another task or process or whatever. But all this is cooperative. If any of those coroutines, threads, tasklets, or whatever, greenlets goes bust and goes like a fault happens. Basically, that fault can bring the whole system down, like the whole node down, because yeah, it's continuous spinning infinitely, and that's it. Even though maybe it's like one of the most non-important parts of the system. I know something happens in, I don't know, an import that or export that happens maybe once per month that is for that guy in the third floor, that only he cares about whatever process. If there's a fault in that, the whole system goes down because the VM itself doesn't give you the isolation necessary to keep the fault contained and your system to continue executing. Okay, so looking at time. So actor model concurrency. Long story short, basically actors, processes on the Beam are isolated from each other. Literally, each one is basically they have their own heap, their own code stack, and their own garbage collector. Right? They are really lightweight, like 300 bytes each. That means on a kilobyte, you can run like 3 of them, megabyte, 3,000, right? On one Erlang Elixir node, you can have millions. Let's say medium-sized applications have at least tens of thousands of them. And what's really important, as I showed previously, they all run concurrently, they are preemptively scheduled, and automatically they use all your cores. Right now, what's pretty sad to me with the whole Kubernetes story, right? We tried so hard to make our systems better and better and use the resources the best way we can. But then you put them in Kubernetes and you say, okay, max CPU 1, exactly. So automatically you just put your system like 22 years ago. Like we pretend that, okay, we have like go routines that and go routine that. and then at some point you put it on one CPU. It's clear that at that point you can have only one. So you're, as I said, pre-multi-core era, right? Your system basically executes as it was 2000s, and I don't know, Disco was a thing. Okay, you have a bunch of processes. How do you compose them? Well, the only way to actually communicate between them is by passing messages. What's important to note is that these messages are not like pointer types, right? Actually, each time when you send a message from one process to another, that message by itself is copied. So it goes from this heap, it's copied directly on another mailbox for the next process. Okay, everything in Beam runs inside processes. Okay, each process, each actor has like a mailbox. And basically, when you're sending a message to another process, it's like a queue, right? Automatically, the message goes into queue. And the job of that process is just, I'm consuming messages from the queue. And based on whatever logic I have there, I'm sending messages to other processes. Right? And yeah, what's really important is this thing. So there's no stop the world thing happening ever, because each process has its own garbage collection. What's even more interesting, if you program properly with processes, one, you're not thinking about processes necessarily as objects in other languages, but if your processes are, the lifespan of them is quite short, right? Okay, I spawn a process, I'm doing like an API call, I parse the response, slice and dice, whatever I want to do with it, and then at that point I say, okay, this process is done, send the result to another process because maybe that does, I don't know, metrics or whatever, map reduce operations. That process that just was destroyed, it is not even required to be garbage collected because the memory is just freed, right? And when you have this, basically, there's no overarching garbage collector that automatically stops everything. Oh, now you want like a real-time system, but right now I have cleanup to do, you know? So that's, and there are a lot of approaches how to try to make our garbage collector better and not stop everything, but yeah. And I mentioned like threads are evil, like are really evil because they break the first rule, right? Threads are not isolated because thread by default, like even from an OS level, right? The definition of a process is something that the memory and everything is isolated. Threads, the definition of a thread is that it shares memory with other threads. So automatically you don't have isolation. When you don't have isolation, you need to lock, you need to, you know, the drill, right? But long story short, it's messy out there. Okay, let's see. We have this nifty Beam. I didn't even give like a lot of, how to say, details about Erlang syntax, stuff like that, or Elixir. And I think it's not even relevant that much for the discussion, because what's important to know is like the runtime itself, how it runs and what's good about it. And first is that it gives you isolation by default. And when you have this, then, as I said previously, a lot of good stuff come after it, right? And yeah, basically here we have two processes. We have process A that what's doing is basically calling send, it's just sending a message to another process, and whatever is like you want to send there is like a list, a dictionary, I don't know, a binary, a string, whatever, right? And then the process, so the other process, all the execution basically is just a receive loop where it keeps reading messages from the mailbox. Okay. Concurrency, yes, they are massively parallel and concurrent. Parallel as long as you have more executing units than one, more cores than one. And what we see here is like with spawn, basically you create a new process. It's almost like, I don't know, in OOP languages saying new, right? But you create a new process and you give it like a function to execute in that process. With pit bang message in Erlang, this is Erlang syntax. The other one, the send, is Elixir syntax, just to confuse you. Pit bang message actually sends like message to that pit. And then both processes actually might end up in a receive loop, because if I send a message to process B, then process A automatically enters in a receive loop, waiting for a response from process B. If it wants a response from process B. If it's not waiting for a response from process B, that means automatically it's like, let's say, asynchronous, right? If you automatically enters like a receive loop, we try to mimic synchronicity. If not, it's like asynchronous communication. And process B, it will have kind of the same receive loop based on whatever pattern. Okay. Yes. Yes and no. Agree.
Actually, it's a receive block, and we make it a loop if you recurse.
Yeah.
Yeah.
Failure detection. Yes. Actually, the Beam has two really strong ways of detecting failures. One is links, the other one is monitors. And you can think about it, if you start a lot of processes, but all these processes, you know that they kind of execute chunks of whatever computation you want to execute. And one of them has a failure. The same thing at that moment is to say, okay, stop all these processes, restart them, right? And links allow you to do that. Basically, if process A links to process B and process B links to process C, if process C dies because of a fault or failure, automatically process B and A are killed as well. And then you have other processes that their own job is just to monitor whatever processes were killed and restart them. And we're going to talk about supervisors. Okay, as I said, what's important and monitors is kind of like a link, but instead there's no how to say. Basically, the process won't die. You just get like a message, like a special message. By the way, you monitored process C. The process died because of failure, and process B will just get a message. Process C died, and this was, I don't know. You can customize actually what is being sent. You can actually take like stack trace, whatever was the state of that process, and just send it to process B if you want. Okay, and yeah, as I mentioned, if what's important is also that all these monitors and links work across machines. So it's not only like in one node. So actually, you can monitor processes from other machines. If your nodes are in a cluster, automatically you can do this. So this speed that you see here, basically, it's like a network address in a way. Just that what's special about it is that it's network transparent, meaning I can have feeds from, I don't know, a cluster in US and one feed from a cluster in Asia. And when I'm sending messages to that feed, it will just go, right? I don't have to think that if it makes sense, it should make sense. But basically, it's just a feed. If it starts with 0 dot, then you know that it's a local process. If it's something else, then automatically you know that it's another node, not a local. Okay, failure detection. Continue as I said before. Usually you have a bunch of processes, but you don't have them to be just this, how to say, soup of processes that are not organized in any way. In your application, it's like on the Beam, usually you organize, not usually, you have to organize them like in a tree where you have supervisors, which the only reason for them to exist is just to monitor our processes, detect faults, and depending on the strategy being used on the supervisor, decide. For example, okay, we have the supervisor on the left monitors 3 workers. If one of them dies, depending on the strategy, we can either restart only that worker, restart, if the middle one dies, restart maybe the one on the right, or we can say, okay, no, all the workers have to be restarted. That's under me, right? So, and yeah, basically there are around 4 or 5 different supervision strategies. But this is actually, if I miss something in any other language VM that I'm working with, it's this, like the fact that you don't have supervisions and you don't have monitors and links. And yeah, for example, in Golang, okay, Go routines are nice, but they are anonymous. They don't have a PID. You cannot send messages to them. You cannot monitor them. You cannot restart them. So it's, yeah.
Can you build something similar?
Yes. But I have a slide for this. Okay, and fault identification, it's pretty clear as well. Basically, when, for example, if the process that we just spawned dies for whatever reason, then the current process that set up like a monitor for it or link will get like a message of this type, like exit, PID, and the reason why it died, right? And automatically you can decide, okay, should I, for logging, yeah, definitely, but should I actually, I don't know, maybe create an alert for PagerDuty, restart the process, whatever. Right? And actually, this is the mechanism used by supervisors, because this process flag trap exit usually is used by supervisor processes where they say, okay, if you establish multiple links, as I mentioned, everything dies that if one of the processes crashes. With trap exit, any process can signal, oh, by the way, I am like a supervisor kind of process. I won't go down. I'm going to continue executing, and it's my job actually to decide what to do. Okay, live code upgrade, yeah, obviously, because otherwise I wouldn't have talked about it. But yeah, in Erlang, you can take processes and upgrade them as the system runs. What that means is that at any time, you can have two versions of the same module executing in your application. And yeah, demo soon. Checking time, I'm on time. Yeah, stable storage, as I mentioned, is not something necessarily to brag about. What's interesting actually in the Beam is that, okay, you have Ninja, which is kind of like a SQL kind of database, but not really. What's really interesting about it is that it comes automatically with cluster replication, and also everything can act as Redis, where you say, okay, I have everything in memory, so it's like in memory cache, but whatever I have in the cache, it's automatically stored on disk and cluster available. Okay, and yeah, RDS and Dynamos and whatever Google. I'm not that familiar with like GCP, but you get the gist. Basically, storage is kind of whatever cloud provider you're using. They offer this like built-in. One interesting solution here is RAEC. Is not that say used anymore, unfortunately, because Basho kind of is extinct now. But what was important for RAEC and unique, I would say, if you knew that your cluster of like storage has 3 machines, like 3 nodes, you could choose for each write that you do the number of replications. You can say, okay, so I have to store this account number. I consider it written actually only when I get back that all the machines, all the nodes in the cluster actually have that value. So you could, for each write, you could specify, for this is not this important, maybe it's just a log. If it's okay for me, only if it's like stored on 2 nodes. But if it's like for really important data, you can force at the time of write, this needs to be replicated on 5 machines. Okay. And basically right now, as you would do like a DB call, you get the result that okay, it stored the value when the replication completed. Okay. Okay. So actor model in the world, back to what you were mentioning. And then we have like 10 minutes for the demo. So what's really important to note is like, one, Beam is this kind of, how to say, it's criminally underused because it has so many good properties that basically any live system right now kind of try to mimics with, I don't know, either Kafka or RabbitMQs and Redis on top of it, and retries, and then you put Kubernetes, and then you have load balancers and everything. So that doesn't mean that you don't need Kubernetes or like you don't need load balancers and everything, but a lot of the complexity required to build fault-tolerant systems is solved in a simple way in Erlang, and the rest of the ecosystem tries to have parity by just putting more. They're saying, okay, but as we know in engineering, any problem can be solved by just adding another layer of complexity on top, right? So, and it's really hard actually to keep systems simple and understandable, and where you don't need a team of DevOps, dedicated team of DevOps just for your system to be alive, right? Terraform that and Pulumi that, and yeah. Okay, the idea is on .NET you have Orleans. This library I think is more than 10 years old. In Golang you have proto-actor and 3 other options to kind of have like actor model. On Scala you have Akka, which is quite old. Also is like 15 years old or something. Pony. What's interesting about Pony is like a language kind of trying to do what Rust does, but it's older than Rust, but it's also using actor model. The only difference, or the big difference, is that it doesn't offer that big of like, or they try to give you isolation in a different kind of like Rusty way, which is good because actually it's really, really good for not soft real-time systems, but actually for real-time systems. But yeah, it's pretty niche. And also, all I mentioned here, like isolation and concurrency and everything, right now, or kind of more or less kind of all those software, or at least the backends that we do, run on Linux, right? And when we run on Linux, Linux, like in the last 10 years, spent a lot of engineering power and smart people trying to replicate what Erlang already does, where they try to offer you like a completely fair scheduler, right? And these completely fair scheduler and C groups, it's actually what powers like Docker and what powers Kubernetes. And when you set memory limits and when you set CPU limits, the Linux scheduler and kind of, like, let's say, functions, as I mentioned before, for the bean. So in a way, basically, Erlang VM, doesn't need necessarily like OS. There's a thing which was called Xen, where basically we're just bootstrapping directly from the bootloader, no OS involved. While, okay, as I mentioned, you can try to have the same with a bunch of other building blocks, and then you play the Lego dance. Okay, but yeah, and right now this one, not that this is winning. This is what's being used a lot right now, but by the whole world except bean systems. In the same time, you have WhatsApps, you have mobile traffic. In the whole mobile traffic in the world, 50% of it runs through Erlang. You don't know, all the Cisco routers, they use Erlang for their routing. There are a lot of, at some point, someone mentioned that Erlang is the best kept secret of the IT industry, mainly because people that are using it, they don't really want that to be known, because it's an advantage for them. And okay, I won't get here. Let's do the demo. We have like 10 minutes, so I want to show you some code as well. Okay. And yeah, any questions before we go to the demo? Hopefully it wasn't too, I don't know, controversial what I've said until now. But you can convince me otherwise for beers and stuff. So I'm okay. Let me 1 second, please. I should have cleaned up my stuff here. Okay. So what we want to achieve here, right? So basically, I'm not sure. Did any of you saw like Soul of Erlang talk by Sasha? It's the same kind of demo. I have a different one, but that one is a bit more messy. So this is simpler for people that don't know what I'm talking about. So basically, at this point, right, we have an Erlang application. I started one node of it, right? And if I go to localhost 4000, right? The whole interface here. What? Go away. So all it does, like, it knows how to sum numbers, right? It's not interesting at all, Right? What's interesting though is that one, I can have errors, and yeah, that's about it. What's actually unique about all this, right? Phoenix is this web framework for Elixir that basically, you build web applications with it. Docker. But what's interesting is that automatically now comes with a dashboard, now being the last 5 years, I think it's like 5 years old. But before you used to have this by connecting directly to the node, and then there's a tool called Observer for the Erlang world. But here, basically, you can automatically see, like, okay, memory, metrics, whatever. But this is the list of applications that are started on this node, which is interesting to know. One is like my application, I think is called My System. And this is like the supervision tree of that, of my application. And you can see here, like, okay, what kind of processes are started and stuff like that. And two, I have also access directly to like the processes themselves. I can see, okay, what P they have, what was the initial call, what the amount of memory they're using, and the number of reductions. And this is like an important bit that I didn't mention at all until now. I mentioned that fairness stuff, where I said, okay, you have a process that preemptively scheduled. That means, okay, when a specific number of whatever happens, then it's stopped and a new process runs. It decides when to stop the process, either one on like I/O, if it has to wait for I/O, automatically the process is yielded, or on the number of reductions. And the number of reductions, basically, you can think about it, it's like a counter, where, okay, I execute the function, +1. I execute another function, +2. You get the idea. And when it reaches like 4,000, I think is now like the number of reductions, automatically, if this process executed 4,000 instructions, whatever those instructions were, it stopped. Another process continues. And it's important that we have access to this. So automatically, just from this dashboard, we can identify heavy processes. Like, do we have something, I don't know, weird happening in the system? You just look here, order by reductions. And so, okay, this process, why is having this big reduction number? It shouldn't, because it's not that heavy as we designed it, right? And we're going to see exactly this, how we debug this. So we have this counter, right? Nothing fancy. But if I start doing shenanigans like this, where, I don't know, this is a pretty big number. And let's just say that my summing algorithm was not format grade, like grade of, yeah, you get the idea. Basically, I just did like +1, +1, +1, then an infinite loop. And it's going to take a while to do this. What I didn't show you here, right? Besides this, we have this scheduler, right? And by default on this machine, probably I have, I don't know, a lot of cores, 10s at least, right? But I forced the scheduler for this node, for this Erlang node, to be 1, just to show you how important it is to have proper isolation, right? Because, okay, now my scheduler continues, it's like 100%. Theoretically, in any other system, when the process is like eating 100% of your CPU, the process is done. Meaning you cannot connect to it, you cannot open a shell into it, anything, because there's no process left, no CPU cycles left to do anything on the process, right? But here we can do, okay, let's start. Actually, 10,000 sounds good. 10,000 processes, and yeah, we stably run 1,000 processes, right? The scheduler is maxed out, but we just started 1,000 other execution. The other they don't do anything fancy. In the other demo they were doing, but in this one they just do like another summing up of numbers in a loop, in a tight loop. So they are consuming some CPU also. But at the same time, so I have like a fully maxed out CPU where I can continue adding work to it. And it's just going through. Okay. Now, let's go to see what process actually it's misbehaving. And we have this, yeah, my system MathSum is doing some calc, and it seems to be like in a really, really tight loop, right? So it spins like crazy. What I care about here, though, is like this speed. This is the process identifier. Here I can get a bunch of other, like what's the call stack, the heap size, all the stuff. And also what's interesting is like the line, right? In the code where it's actually spinning. It's like line 28. We are going to fix that rather sooner than later. But let's think about right now, we are in the situation where we are operating, we are on call, and we get an alert that, okay, max CPU 100%. We look at it, we don't want to restart everything because those 10,000 jobs are doing valuable stuff for us, right? So we don't want to do like a node restart. We identify this process is misbehaving. Instead of like doing like kubectl, I don't know, either restart the pod or stuff like that, we can just go and connect to the node. One second. Actually, sorry for that. It's great, but I care about this actually. Sorry. So basically, right now I have the PID of the process, right? And I can automatically check some information about the process. And what I mean by that, okay, we can check, okay, what's the code stack. Basically, I kind of see more or less the same information that we saw in the dashboard. But I also built one time a trace, a function, or better said, such a build. But when we see, like, we can trace the process, where you can say, okay, trace each, not each, like 50 invocations of this process. And we see that something went really wrong, right? Because, okay, it's clear we have like a number that keeps on spinning, and it's not really obvious what's happening there. But as operators right now, we don't want to fix it, right? We are on call, it's like middle of the night. I won't do a hotfix right now in production. I just want to stop this, right? So, sorry. Yeah, sorry.
So we lost.
As
We
yeah.
lost
The share. You sure? Sorry. Oh, one. No. Oh, okay. For you, it was so interesting. Okay. What? 1 second, please. What? Okay. Let's. Yeah, it's not fault tolerant. Okay. Let's do it again. Sorry. Okay. Okay, it's kind of working now. Sorry. Okay, so can you see it now? Yes. Okay, sounds good. So basically, we traced with runtime trace. But now we have the process. We identify that, okay, this process is doing some shenanigans. Something is definitely wrong with it, or we want it to stop, right? So what we are doing is like we just stop the process. Right? We process kill, we process exit, and you can specify the exit reason. This is like -9 in Linux. Right? And what's interesting to see here is that because the processes are isolated, the process that connected from the front end to my back end and actually started the computation, and the computation, I killed it, right? That process is gone. Still, the process that connected the front end was able to detect that fault happened, and it's properly showing on the front end, okay, it's the fault happened, okay. The process doesn't exist anymore, yes. And if you look at the scheduler, right, automatically, like the CPU went down. Our system keeps on chugging. It's okay, right? The second error, right? So, okay, fix this. Nice. Okay, so we have this 42 as well, right? But what's let's fix it again. Actually, no, we seen it. Basically, now we have a running system.
The screen is not moving. I think you should stop sharing.
Okay. Sorry. Sorry, no, it's not. Yep. Screen. Hopefully, is it better now in online? Yes, awesome. Okay. So I should have closed the tabs. Sorry for that. So we have these errors, right? Now it's morning. We are no longer on call. I'm the next colleague that actually has to fix this mess. We have errors in our system, right? So we go we try to fix them. And I know that this is implementation for our super duper fancy math implementation. We see that, okay, for 42, yeah, this is easy fix. And also we want to fix this 99999 multiples of 9, right? And if you apply some maths, like 4th grade maths, we should be able to fix that as well. And because I'm lazy, I'm gonna just copy the fix. Because yeah, I mentioned I'm lazy. And also not for you to actually see me trying to type something. Okay, so yeah, this goes away. We have a same implementation for sum now, right? Just doing like, I don't know, multiply by n plus 1 divided by 2. Okay, so we have this, but we have our system which is live, and we do not want to stop it, right? So first, I'm going to stop this shell because I don't care about it right now. Actually, oh, great. Okay, let's see. Awesome. Could not compile.
It had 2 parameters before.
It had 2 parameters. Yeah, 1 second. Actually, just to be sure that I got some. Okay, because it was like color and 1 second. Basically, we just you see why I said that I'm gonna actually copy the code, because not to see me type, but here we are. And this should work, I think. Maybe. Yeah. So, okay. Okay, not sure what happened there, but you get the idea. Yeah. Okay, so let's see, 42, it works now. By the way, it's important to see we didn't stop the system. Our processes are still processing whatever they were doing before, right? I fixed the error, and if we give it like a really, really big number, it's also computing instantly. Okay, and the second part of the demo, it's, come on, go away, please. Okay, and this is gonna be, we add one more node, we create a cluster now. Until now, we had only one Erlang node with one scheduler. I showed you like how important the isolation is, so we can actually react to faults and live code upgrade our system. And now we have like another node. And automatically we see that the jobs dropped to half. That means half of the whatever we were processing, they were moved to the second node. Basically, it's automatically balancing. And if I connect to localhost, this is the other node, like the one we just spawned. We see that, okay, basically more or less has half of the processing, right?
Dynamically Find out how many.
Yeah, so yeah, basically we have a loop that looks each time, okay, how many nodes are in the cluster. Based on that, decides what's like the scaling factor, how many jobs should be on this machine, and then automatically balances them.
Trying to report to send. No,
Yeah, so you are asking about EPMD, right? Yeah, names. So this or not, or like the 4001, yeah, it's just automatically increments. So no, it's the same logic kind of here. The you know.
And it's the command mix add node was something you wrote.
It's yeah, it's custom. But basically, what's important to know, like Elixir, not Erlang. Mix is like a project kind of tool, like CLI for Elixir. Comes with a predefined set of tasks. I know Phoenix framework comes with a set of tasks, but then you can write your custom ones. And the custom ones that you are interested, actually this one, which if you look, one, it checks exactly the command that I checked, like EPMD names, looks how many nodes are in the current EPMD daemon, and then for each one, actually just increments the, yeah. Then actually starts the node, right? Because automatically it appends like the name, it's different. Because like here, you see like system 1, then system 2. If I start another one, it's gonna be, yeah, obviously. Right, so now we have 3 started. And automatically we see that yet again, another drop. Now like the proper number of jobs on a node would be 3,000. Okay, this is nothing really fancy. I had fancier demos, but for tonight, I think it's okay. And by the way, this code is not mine. You can find like the repo online, or maybe I'm gonna post it to the meetup, like the slides, and then like the code that I used. And yes, and actually back to the presentation. Yeah, I showed you just with Erlang. I don't use Docker, Kubernetes, load balancer, stuff like that. It's just like 2 libraries being used, and you can have a lot of the guarantees that usually you would use at least 5 or 10 different tools to achieve. And yeah, this is a quote from Joe Armstrong. Joe Armstrong was one of the creators of Erlang. He passed away a couple of years. But from my point of view, he's one of my heroes, definitely in the IT field. And yeah, try to make code beautiful should be enough. Okay. And thank you. Questions? No, everyone is tired. It's 7 p.m. here. You know. Any questions from online? No. If not, going once, going twice. No. Okay. Yeah.
How come that the other languages are having so hard times to catch up with the
Well, they, how to say, I didn't show you any Erlang code, right? It's not easily understandable if you don't spend a lot of time on it. So my how to say, my journey with Erlang, right? I heard about Erlang. There's this book called 7 Languages in 7 Weeks by Bruce Tate. I read it around 2010, 2009, something like that. And okay, let's learn Erlang. Sounds interesting. And then I saw the syntax, and okay, let's postpone this. And then okay, I really got into like functional programming. I studied F#, then a bit of OCaml, then Elm, and then Elixir happened. And Elixir basically is like kind of a Erlang, but with kind of like Ruby, Pythonish syntax that gives you exactly the same runtime guarantees, everything. It's a mix between like a dynamic language, really nice syntax, and functional programming. And automatically that got me hooked up. I learned Erlang or like the Beam through Elixir. And then actually I worked with Elixir for a couple of years, and then I went to Erlang. And now I think there are things in Erlang, the language, that I like more than Elixir, the language. So yeah, it's way more, the syntax is way more consistent in Erlang than in Elixir. So, but yeah, it's definitely, for a lot of people, it's off-putting at first. It's not this C kind of, but in the same time, right, but this is readable, right? This is kind of looks like Ruby-ish. Basically, Elixir, this is Elixir. Elixir is inspired by Ruby as a syntax. So it's way more grokkable from this point of view. At some point, probably not here. Yeah, it's like modern tooling. And yeah, definitely mix, yeah. Yeah, or better said, there are things in Erlang that are really bad right now. If you look at Elixir from an Elixir point of view, mostly like collections. All the higher order functions that work with collections in Erlang, they're not consistent. They're either basically, for example, here, right? If you look at this code, I have like a string iterate and then a strip map and an enum find. And I'm using the pipe operator, which all it does says, okay, execute this function, take the output of that function, and pass it out as the first increment on the next function. And basically, with the pipe operator, you can chain a lot of executions in a clean way without having this intermediary state, right? Where you say, okay, var a equals whatever, execute this, then I will take var a, pass it the argument to the next call invocation, right? Or instead of saying parentheses, so you do not have Lisp, right? But basically, with pipes, you can execute things in a kind of sequential way in a nice manner. In Erlang, 1, you do not have pipe. 2, the order of the arguments, depending on whatever higher order functions you're calling, is it like map, reduce, find, filter, whatever, it might be that the argument where you have to pass like the list, like the data, the collection itself, it can be either the first or the second or the last, and because of that, because it wasn't necessarily well thought from this point of view, it's uglier in a way, right? So, but in the same time, there are nice things about it also. But yeah, actually, they do try to keep up, right, or to struggle, right? So they do try so they do try to actually offer but actually right now, even Rust, right, it's kind of like a contender on this, but still doesn't give you this. The isolation is not there, like the way you compose processes is not there, like the transparency across nodes is not there. So that doesn't mean that if you do not take whatever C variant, you cannot build this, because Erlang is built on C, right? But you get the idea. It's just that, I don't know, you have to replicate 40 years of engineering. Okay. And yeah, if there are no more questions, thank you. Hopefully found something new, interesting, at least for the people that don't work daily with Erlang and Elixir.
Thank you.
Thank you. Bye.
Let's have some